Welcome to the second part of our first episode in electrostatics, which was basically dealing with the introduction to electrostatics. We want to look at how to distinguish between a conductor and an insulator using an electroscope. Here we shall just give an electroscope a given charge, either positively or negatively, and then what we want to test is brought near the cap of a gold leaf electroscope. Near, not touching. Now, if there is no change in the divergence of the gold leaf, then the material we're dealing with is an insulator. But if the leaf diverges further, then the material is a conductor. So if you observe any change in divergence, then the material you're dealing with is a conductor. But if there is no change in divergence, then you are dealing with an insulator. Remember that when you charge an electroscope, the leaf diverges, the gold leaf diverges. So if you bring what you want to test near the cap of that gold leaf, which is already of the GLE, which is already charged, and you observe a change in divergence, then you know what you're testing is a conductor. But if the leaves remain the way they are with the same divergence, even when you bring that material you want to test near the cap, then we conclude that our material we're testing is an insulator. Charging a body negatively at zero potential. Charging a body negatively at zero potential. How do we do it? When you want to charge a body negatively, we said it's done by induction. We said we must use a positively charged rod as the inducing rod. So we bring it near the end of the conductor. When we bring it, of course, which is standing on an insulator, when we bring it near the end, the negative charges are induced on the end that is near the inducing charge, and the positive ones are repelled to the far end of the neutral body, as we have seen before. Now, we're still holding the inducing charge in place, that is the positive glass rod. Our conductor is earthed. You earth it, or you simply touch it momentarily. Then afterwards, you break the earthing while still holding our inducing rod in place, and therefore our object is said to be charged negatively at zero potential. We also want to look at the electrophorus. An electrophorus is a device that we can use to provide an unlimited supply of positive charge. It does not produce energy, so it isn't a source of energy, though it is fond of converting mechanical energy into electrical energy. I'll be seeing how this is done. Now, the electrophorus basically consists of an ebonite base, which we can easily charge negatively by rubbing it with the duster. After charging the base negatively, we bring a metal disc which is attached to an insulating handle. We bring the metal disc and place it on top of the negatively charged ebonite base. As you can see on the screen, the ebonite base has been charged negatively by rubbing it with a duster. When we bring the metal disc and place it on top of the ebonite base, it will induce a positive charge on the bottom of the metal disc and repel the negatives on the far end or upwards. Then we shall get our earthing wire, or we shall earth the metal disc. When the metal disc is earthed, all the negative charges, the electrons, will escape from the metal disc to the earth. Now, when we break the earthing, we remain with only the positive charge on the metal disc, which we can transfer where we want it to be transferred to, and then we can repeat the process with the same negative charge that we gave the ebonite base. we can repeat the process and produce as much positive charge as possible. That's why we say the electrophorus provides an unlimited amount of charge. We also want to discuss the distribution of charge over the surface of the conductor. But first of all, we need to define the term surface charge density as the quantity of charge per unit area over the surface of a conductor. Surface charge density is the quantity of charge per unit area of the surface of the conductor. In other words, surface charge density is charge over quantity of charge over surface area. Of course, it is coulombs per square meter as units. Now, it has been discovered that charge is mostly or always concentrated at the sharp points. In other words, we find more charge or a higher charge density at the sharp points of the conductor compared to the points which are not so much curved as the sharp points. If you look at a spherical conductor, a sphere has no sharp ends, so its charge distribution is uniform across the whole conductor. If you look at one which is triangular shaped, we discover that we shall be having more charges on the sharp edges than on the flat surfaces. The same thing applies to the rectangular conductor. Then when you look at the pear-shaped conductor, also has more charge density at the sharp point compared to the points which are less curved. Note, charge only resides on the outside of a hollow conductor. If you have a conductor which is hollow, it has been proved through Faraday's ice pile experiments that charge only resides on the outside of a hollow conductor. This has been proved by Faraday in his Faraday ice pile experiments, and that's what I want to talk about here next. Now, to investigate charge distribution on a pear-shaped conductor, I want us to do that one first. Of course, a pear shape. By pear shape, we mean this shape that I'm drawing. That one is a pear shape. It has a less curved surface, like a sharp on one side, and it has a sharp edge on the other. That one is a pear-shaped conductor. Now, we use a device called a proof plane. A proof plane is actually a device used to transfer charge. It is just made of some conducting leaves which are attached on an insulating handle. When you place those conducting leaves over the surface of a charged surface, they always pick up charge which is proportional in magnitude to the magnitude of the charge which resides at that point on the surface of the conductor. Now, this proof plane is placed on the surface of the conductor. Now, a sample of the charge acquired by the proof plane is then transferred to a hollow metal can which is placed on the cap of a gold leaf electroscope. So they get a hollow can, place it on top of the cap of a gold leaf electroscope, which means it almost becomes part and parcel of the gold leaf electroscope cap. So they bring the other proof plane after placing it on the surface of the pear-shaped conductor, then they transfer it to a hollow metal can which was placed on the gold leaf electroscope, and we observe or we note the deflection of the gold leaf. The proof plane is used to pick samples of charges from different parts of the conductor, from the flat ends, from the less curved ones, and from the sharp points, each at a time. And every time it is done, the deflection of the gold leaf electroscope is observed or noted. Now, it is discovered that the greatest deflection is obtained when the sample of charge is picked from the pointed ends of the conductor, like around this point. There you will discover a greater deflection. What I was saying is you have an ice pile which you have placed on the cap of a gold leaf electroscope, That is the cap connected to the brass rod. This is an insulator, and that is the whole gold leaf electroscope. This one has the gold leaf. So when you bring your roof plane, which outside is made of conducting leaves, which are attached to an insulator. So when they are placed like at this point, they will pick a charge, a sum of the charge, but that charge they pick is proportional in magnitude to the quantity of charge at that point. So when they pick that one and you lower that roof plane into the hollow can, it will induce charges on the gold leaf electroscope and will end up repelling opposite charges to the gold leaf and the brass rod and cause deflection. Now, the deflection is what we observe because it depends or it corresponds to the magnitude of the charge which was on the proof plane as it was being lowered, and this charge which the proof plane has is proportional to the charge which was residing on the surface on which it was placed. So, when they observed this with different parts, they discovered that the gold leaf will deflect most when the proof plane has been transferred from points of maximum curvature or from sharp ends or points on the conductor. Now, we also take interest to discuss Faraday's ice pile experiment, which shows that charge only resides on the outside of a conductor. Now, this setup is shown here, whereby we have a gold leaf electroscope is one supposed to study for us the behavior of these charges. We have a gold leaf electroscope. We have a Faraday's ice pile or a metal can, which is placed on an insulating stand. Then they connect the metal can by means of a conducting wire to the cap of the gold leaf electroscope. In some experiments or in some books, they actually place the hollow can on the cap of the gold leaf electroscope. So it's a similar arrangement. The major point here is ensuring that the metal can is placed into contact with the cap of the gold leaf electroscope. Now, when they do this, remember, we get a positively charged metal sphere S and we lower it into the metal can. But we don't allow that charged sphere S to touch the inside walls of the metal can. Now, the leaf of the gold leaf electroscope, of course, diverges. Why? Because when you bring the positively charged sphere, it will induce a negative charge on the inside of the can and will repel all the positive charges. They go through the wire connecting the metal can to the gold leaf electroscope. They are repelled further and you find them on the brass rod and the gold leaf, thus causing a divergence. So divergence happens when you lower that metal sphere S into the hollow can, even if it doesn't touch the inside walls of the metal can. Now, when S is withdrawn, when the metal sphere is withdrawn, it is observed that the gold leaf of the electroscope will collapse because what was repelling the positive charges to that end of deflecting the gold leaf and from the brass rod is no longer there because what was pushing it away has gone. So when S is again lowered inside the metal can without touching it again, the leaf of the electroscope will diverge to the same extent as before, which means there was no transfer of charge and no transfer of charge anywhere. So the same effect which happened before will now happen again when you bring it back and lower it into the hollow metal can. Now, this time round, let us allow the metal sphere S to touch the inside walls of the can. When you target the inside walls of the can, the divergence of the leaf remains unchanged. Why? Because when the metal sphere was lowered into the metal can, it induced a charge on the inside of the walls, which is equal but opposite to the charge on the sphere. So it induced an equal in magnitude but a negative charge on the inside wall of the sphere, and it will repel the positive to the outside. Now, when it touches the inside of the can, the negative charge on the inside of the can will neutralize the positive charge on the metal sphere. But the positive which had been repelled to the outside remains on the outside walls of the hollow can. Now, when S is withdrawn and testing is done, it is found to have no charge. So the S has been discharged by the own by the opposite charge which it had induced on the inside of the can, which was equal in magnitude but opposite to itself. Now, there must have been a charge inside the can equal but opposite to the charge on the sphere as I have talked about. Since the leaf remained diverged, the charge on the can now is residing on the outside of the can, and this charge is equal to that which was originally on the metal sphere S. Let us now talk about action at sharp points, or what we call corona discharge. You'll allow me use a pear-shaped conductor for reference. Now, this pear-shaped conductor, we said, it has a uniform distribution of charge on the less curved surfaces and a very high concentration of positive charge or of charge on the sharp ends of the conductor. Now, the high concentration of charge or the high charge density or intensity at the sharp points of the conductor will cause the air molecules around this sharp conductor to become ionized into ion pairs, negative and positive. So the high electric field intensity at the sharp points of the conductor will cause the air around to be ionized or to break down into positive and negative ions. Now, the positive ions, or the ions which are similar to the ions on the sharp points, will be pushed away or repelled away at a very high speed, and as they move, actually they constitute an electric wind, which sometimes is even strong enough to blow a burning candle. Now, the charges which are opposite to the charge on the sharp ends of the conductor will be attracted. So as they attract those negative ions, in this case, they will come and neutralize the charge which was on the sharp points. So when they do so, the conductor ends up losing some of its charge through what we call corona discharge. So that is what we call corona discharge. Now, let's look at application of action at sharp points, applications of action at sharp points, or applications of corona discharge. Application number one is lightning conductor. The lightning conductor is a device that helps to protect tall buildings, boosters, and other tall installations from being destroyed by lightning. But before we discuss that, I would like us to discuss how lightning destroys a building. When clouds are in motion, they become charged due to friction as they rub against one another. They become charged due to friction. Now, the resulting charge builds up, leading to a high potential difference between the clouds and the earth, because the clouds are now charged and the earth is not. So, because of that high difference in charge, we have a high potential difference between the clouds and the earth. Now, because of this, current is easily expected to move at a very high rate, what we call discharge currents. They move from the clouds down through the buildings. Remember, our buildings have got a very high resistance because they are not conductors. So when that large quantity of discharge happens through a building which has a very high resistance, it will generate heat in the walls of the buildings, and the building can easily burn down because of lightning. Now, to avoid this phenomenon or to protect our buildings against being destroyed by lightning, we install and use what we call lightning conductors. Some others call it a lightning arrestor. Now, this arrestor is of course got by just installing metal spikes, sharp spikes at the top, possibly at the sharpest point of the building, and then connecting those sharp spikes by means of a copper strip to a copper plate, which is often buried underground. Sometimes they bury it using salt and others and charcoal and the rest, but all the aim of burying it with those things is to increase its level of conductivity between it and the earth, because it's our aim of this whole setup is to safely conduct away charges which might have destroyed or burnt our building through conducting through the non-conducting walls of the building. So we are giving the charges a safe passage where they can pass through and be dissipated to the earth without necessarily causing havoc or burning the building. Now, when a negatively charged cloud approaches a building and it finds these spikes there, what happens is that it will induce a high positive charge at the spikes and will repel the negative charges to the ground through the copper strip. Now, the very high intensity of positive charge at the spikes will ionize the air around the spikes. In other words, the air which was neutral previously, the molecules in the air which were neutral previously will be broken down into negative and positive ion pairs. Now, the positive charges will be repelled to the negative cloud and they will neutralize the cloud. Whereas the negative charges will be attracted to the spikes and they will neutralize those spikes and discharge them. In so doing, the electrons are connected separately to the ground through the copper strip as we began the explanation, and therefore even our cloud is discharged safely without causing any havoc or burning our building. Now we need to talk about the Van de Graaff generator. The Van de Graaff generator, I have drawn one here. It is in pink because this one was poorly drawn. So I have drawn for us another simplified one on the right in pink. So we have an electric motor M. Its work is to drive the lower pulley, which in charge will drive the upper one. And we have a silk belt running over these pulleys. So the silk belt will be in continuous motion into and out of the metal sphere S. Now the metal sphere S stands on insulating tubes not shown fully in the diagram. So it's not touching the ground and it is not allowing flow of charge or escape of charge through the other part because of the insulating stand. Now we have two electrodes. Electrode 1 is kept at a very high potential, positive potential, almost 10,000 volts. And the electrode E2 is connected to the metal sphere. Now this is what happens. At electrode E1, because of the high positive charge density at the spikes of electrode E1, the air around electrode E1 will be ionized or broken down into positive and negative ions. Now, when this happens, remember, now we have positive ions on the spikes of E1. The air has been broken down into positive and negative ions. Now, these ions which have been formed around electrode E1, the positives are repelled or pushed away by electrode E1 onto the belt. Remember, the belt is in motion. It carries them up into the metal sphere. Whereas the negative ions which had been formed are attracted to the specks of electrode E1, they go there and they neutralize the charge there. But however, our high potential battery here is still charging our specks E1, so it is a repetitive process. Now, the ones which were spread, the positive ions which were spread onto the belt by repulsion are carried up into the metal sphere. But at the end of the metal sphere, now our belt is moving. Our belt is moving upwards in this motion. Now, as our belt reaches electrode E2, what happens there? The high positive charge on the belt will induce a negative charge on the spikes and will repel positive charge on the space of E2 and will repel the positive charges onto the metal sphere S. Now, the high charge density of negative charges on electrode E or E2 will ionize the air again around E2 into positive and ion pairs. The positive ion will be attracted to the specks of electrode E2 and neutralize the negative charge which has been formed, whereas the negative charges which were formed by ionizing the air will be repelled or pushed onto the belt and will discharge the positive charge which came with the belt before the belt goes over the second pulley, and we keep on repeating the process. So every time that cycle repeats itself, more positive charge is repelled to the metal sphere, and therefore we shall be able to generate enormous amounts of positive charges on and keep them on the metal sphere almost up to 1,000,000 volts relative to the earth. So this has been an introduction to electrostatics. Watch out for the next episode, episode 2. And in episode 2, shall be discussing the Coulomb's law of electrostatics.